Hello students, in this video we will see how to solve a numerical problem based on the actual gas turbine cycles or actual Brayton cycle. For that purpose we have a question.
In an oil gas turbine installation, air is compressed from a pressure of 1 bar and temperature of 300 Kelvin up to a pressure of 5 bar. The oil used has a calorific value of 42500 kg per kg and the combustor efficiency is 95%. The hot gases leave the combustor chamber at 1000 Kelvin. The isentropic efficiency of the turbine compressor are 90% and 85% respectively. Assuming the mass flow rate of the gas air is 1 kg per second, then find the air fuel ratio. So first of all, we have to write the given data. Since we know that this is a gas turbine and also it is given in the problem, the turbine and compressor efficiencies are given that 90% and 85%. Hence you can see that this problem is based on the actual gas turbines or actual Brayton cycle. Okay, so we have given P1 is 1 bar, T1 is 300 Kelvin, pressure after compression temperature up to a pressure of 5 bar, so P2 is 5 bar. Okay, and calorific value of the fuel is given as 42500 kg per kg. The combustor efficiency of combustion chamber is equal to 95%. Hot gases leaves the combustor chamber at 1000 Kelvin. Gases leave the combustion chamber at 0.3, that's why T3 is given as 1000 Kelvin. Okay. The isentropic efficiency of turbine is 90% and isentropic efficiency of compressor is 85%. Okay. Mass flow rate of air is m dot is given as 1 kg per second. Okay, take gamma is equal to 1.4, Cp of air is equal to 1.005 kg per Kelvin, and Cp of gas is equal to 1.1 kg per Kelvin. So the idea behind to solve any gas turbine problem is that first of all we have to draw the cycle on TS diagram, the actual Brayton cycle on the TS diagram. After that we have to calculate all the temperatures in the cycle. So let me draw TS diagram. One to two is a isentropic compression and 1 to 2 dash is a actual compression. 1 to 2 dash is a actual compression. 2 dash to 3 is a combustion process. 3 to 4 is isentropic expansion, and 3 to 4 dash is actual expansion. 4 dash to 1 is a heat rejection. Okay, this is P1 equal to P4, this is P2 equal to P2 dash equal to P3. Okay, so at point 1 the pressure is P1 is equal to 1 bar, and at point 2 the pressure is P2 is equal to 5 bar. So you can say RP, that is pressure ratio, is P2 by P1 is equal to P3 by P4 is equal to 5 divided by 1 is equal to 5. Okay, so we have to calculate temperatures at point 2, 2 dash, 4 and 4 dash. Okay, for process to calculate temperatures at point 2 we have to use isentropic compression process in the compressor. So process 1 to 2 is a isentropic compression. Isentropic compression in the compressor. So let me use the isentropic law. T2 by T1 is equal to P2 by P1 or Rp to the power gamma minus 1 over gamma. So put the value of T2 is equal to T1 times T1 is 300 Kelvin, Rp is 5, gamma is 1.4 minus 1 divided by 1.4. After calculating, you will get T2 is equal to 475.15 Kelvin. This is T2. Okay. So now you have to calculate T2 dash. T2 dash is calculating with the help of compressor efficiency. So use the compressor efficiency. You can write compressor efficiency as neta C is equal to T2 minus T1 divided by T2 dash minus T1. Okay, this is the compression efficiency. Okay, it is given as compression efficiency is given as 85%, so it is 0.85. Okay, so put the value of T2, T1, and you will get T2 dash is equal to 506.06 Kelvin. This is T2 dash. Okay, now we will find the value of T4 and T4 dash. So to calculate T4, you can use the isentropic expansion law. Process 3 to 4 is a isentropic expansion in the turbine. So you can use T3 by T4. T3 by T4 is equal to Rp to the power gamma minus 1 over gamma. So from here we can write T4 is equal to T3 we have known, it is given in the problem. So write the value of T3 is 1000 multiplied by Rp to the power, Rp is 5 to the power 1.4 divided by 1.4 minus 1. Okay, so we get T4 is 31.39 Kelvin. Okay, so after T4 we have to write the turbine efficiency, isentropic efficiency of turbine. From there we will calculate T4 dash. Okay, so T3 minus T4 is a isentropic expansion divided by T3 minus T4 dash divided by T3 minus T4. Okay, so it is given that isentropic efficiency of the turbine is 90%, 0.9. So put the value of T3 is 1000 Kelvin, T4 dash we have to calculate. T4 is calculated, so put the value in this equation. T4 dash is equal to, we get T4 dash is 668.25 Kelvin. Okay, so now we have calculated all the temperatures of the cycle. Okay, so first question you have to calculate air fuel ratio. We have given mass flow rate of air and calculate the mass flow rate of fuel and divide the mass flow rate of air to the mass flow rate of fuel, we'll get the air fuel ratio. Okay, so in between 2 dash to 3 there is a combustion chamber in between 2 dash to 3. From here the fuel is supplied mass flow rate of fuel. You have to calculate mf dot. Okay, mass flow rate of air is entered in the combustion chamber and mass flow rate is entered in the combustion chamber. Combustion takes place in the combustion chamber. We'll get the mass flow rate of gases. mg dot is equal to the ma dot plus mf dot. Okay, so at point 3 we have temperature T3. At point 2 dash temperature is T2 dash. So we have to balance the energy balance in the combustion chamber. Okay, so you can write heat supplied in the fuel is equal to the heat utilized by the gas. Heat is supplied by the fuel, heat is utilized by the air, and it converts into the gases. Okay, so heat supplied in the fuel have the energy, mass flow rate of fuel multiplied by its calorific value. This is the energy supplied by the fuel. Since we have also given that there is a efficiency of combustion chamber, 95% is efficient, so we have multiplied by efficiency of combustion chamber because there are 5% losses of heat through the walls of the combustion chamber. Heat utilized by the gas after the combustion, energy is mass flow rate of gas multiplied by T3 multiplied by Cp of gases mCp delta T minus before the entry to the combustion chamber mass flow rate of air entered multiplied by temperature is T2 dash multiplied by its specific heat mCp of air. Okay, so now you can put mg dot equal to ma dot plus mf dot. Okay, put the value of cb is given as efficiency is given as T3 we have calculated, Cp of gas is given, Cp of air is given, T2 dash we have calculated, ma dash is given as 1 kg per second. After putting the data from here, we will get mf dot mass flow rate of fuel is given as calculated from the equation 0.015 kg per second. After calculating, we will get the mass flow rate of fuel. So you can write first part mass air fuel ratio is equal to air is 1 kg per second, mass flow rate of fuel is 0.01505. You will get air fuel ratio as 65.54. Okay, second part, you have to calculate power output of the plant. So okay, so in a second option we have to calculate power output of the plant. So we know that power output or work W net is equal to the work at the turbine minus work supplied to the compression. This is the net work done or power developed at the plant. Okay, so W compressor is written as Cp of Ma dot multiplied by Cp of air multiplied by T2 dash minus T1. Compression work is T2 dash minus T1 multiplied by Cp of air multiplied by mass flow rate of air, because in the compressor there is only the mass of air which is compressed. Okay, after putting the value you will get the compression work is 207.09 kilowatt. Okay, and similarly we can calculate turbine work is equal to the mass flow rate of air, mass flow rate of gases mg
dot. In the turbine, there is expansion of gases multiplied by Cp of gases multiplied by T3 minus T4 dash is the actual expansion. Okay, on putting the value in this expression, we will get the turbine work is 307.49 370. Okay, 370.049 kilowatt. Okay, so we can write the net work done is W net we can write turbine work minus compression work, W turbine minus W compression, both we have, and after putting the values of turbine work and compression work and subtracting, we will get the net work done is 163.4 kilowatt W net. This is the power generated at the plant. Okay. Finally, we have to calculate the thermal efficiency of the plant. Thermal efficiency of the plant. Thermal efficiency, we know very well. Output is W net, power developed at the turbine, divided by the heat supplied. Heat supplied, we have calculated that heat supplied is MF into CV. We can write W net divided by MF into CV. This is the heat supplied multiplied by efficiency of the combustion chamber. We have given that efficiency of the combustion chamber is 95% combustion chamber. Okay, on putting the value of all these, we will get the efficiency is 26.52%. Okay, this is the value of thermal efficiency of this thermal power plant. So the main idea to solve such kind of problem is that we have to draw, first of all we have to draw the TS diagram showing all the processes including all the temperatures. Okay, after that we have to calculate all the unknown temperatures with the help of isentropic law and by using the compressor and turbine efficiencies.